Thank you very much for your very nice and talk contribution and talk. And we can I can ask you at the end of the session probably, or if not, we can just try to organize these post discussions for everyone interested and so on, right? But we discussed this at the end of these two sessions. Thank you very much, Tommaso. Thomas, you are ready, right?
I am ready. I'm assuming that you can already see my first slide and also hear me. So hello, everybody. I would also like to thank Luis and everyone who organized this symposium with him for pushing forward this nice idea. And I appreciated really the selection of speakers is also made in a way to so that everyone kind of connects to each other. And for this reason, I wanted to present some work that actually has emerged from a long collaboration that I was having both with Luis on one hand, and then also with Tommaso on the other. And we heard about Tommaso's stochastic beta relaxation theory already. And in this talk, I want to show you what one can do as an application of it, basically, to tackle the problem of aging in glasses. And okay, never mind the outline, but let me just remind you about one standard protocol that we can have in mind when we talk about the aging effects. And I'll keep it very simple, starting with a hard sphere system, which has initially a packing fraction that I call phi I. And then I imagine an instantaneous quench to a final packing fraction phi f that typically will be very close to the glass transition or above the glass transition. And obviously, if we start from an equilibrated system in the beginning, then we will have to observe the final system for an increasing amount of time to understand how it comes to an equilibrium or stationary state after this rapid compression. And in line, I guess I don't need to dwell on this for too long given the present audience, but in line with mode coupling theory, we will look mostly at density fluctuations. And we are interested basically in understanding the probability distribution function that describes the system that will be a waiting time dependent quantity after the quench. So the probability to find a given configuration at a given waiting time sets these averages that I denote with angular brackets TW. And then one can look at the structural and dynamical quantities, and the simplest one are the waiting time dependent static structure factor, so just the static average of the density squares, or the dynamical transient correlation function that is defined as the average given a certain waiting time of a density fluctuation at TW and a density fluctuation at the time T later. And I particularly wanted to talk about this in this context because there are some rather nice simulations that have been performed by various co-authors that are probably in the audience. Just to see what happens, what you see on the left is actually the waiting time dependent static structure factor for a certain initial configuration quenched to a certain final overall packing fraction, and the different colors are different waiting times after the quench. And this is a zoom in of the peak of the structure factor, and you see this evolves from small waiting times in black to large waiting times. And as we all suspect, in this being a glass, the static structure evolves a little, and the dynamical correlation functions evolve dramatically. So again, here they are shown as a function of delay time, which I call T, for various TW parametrically increasing from left to right. And what you see is that mainly a plateau emerges as the waiting time increases, and the final relaxation time of this function also increases with the waiting time. And we can look at this, we can try to extract the relaxation time, the structural relaxation time of these functions as a function of waiting time. And if you do that in the simulations, you get the plot shown on the left. So you show the alpha or structural relaxation time as a function of waiting time. And different colors here correspond to different quench protocols, all starting from the same initial density. And per color, you quench to a certain final density that is shown here. And you see that if you quench from an equilibrated state to a final state that has a density that is below the glass transition, the system is able to equilibrate, which here you see by the fact that the structural relaxation time becomes independent of waiting time after a while. And this while that you have to wait to reach a stationary state increases and increases. And for the highest densities to which you quench in the simulation, you run out of simulation time before you ever see the leveling off of this relaxation time. You can take the same data and make different cuts. You can basically ask for cuts at constant waiting time, plotting the result as a function of the quenched to density, which is here on the x-axis. So each color in the right-hand plot corresponds to a fixed waiting time. And then you see the typical scenario that we are familiar with for glass-forming systems and experiments of glass-forming systems, that the structural relaxation time seems to increase rather sharply. At some point, you fall out of equilibrium because your waiting time is too small, and you do not follow any longer the extrapolated equilibrium curve of relaxation times, but you observe something that grows more slowly. And I will try to come back to these two plots and show you how we can rationalize them. And the way to rationalize them that I want to talk about and put up for discussion is essentially a combination of the non-equilibrium self-consistent Langevin equation theory that we will hear about in the next talk by Magdaleno, and the scaling laws of mode coupling theory extended to the scaling laws of the stochastic beta relaxation theory that we just heard about. The first ingredient is we need an equation that describes the waiting time evolution of the static quantities and then also the dynamical correlation functions. And Magdaleno will show us an approach based on an extension of Onsager's theory. I will basically use those equations, but just for fun and also to put it up for discussions, I present a very sketchy alternative way of arriving at them that I owe to Matthias Fuchs, who's also in the audience, who developed it with Mike Cates in aiming to describe or to develop a mode coupling theory for colloidal suspensions under shear. And so the formalism is called integration to transients. And you can start off by saying it's basically a formal solution of the evolution equation of the probability distribution function of the system. So typically, depending on the dynamics that you choose, the probability distribution function with which you form statistical averages evolves a partial differential equation. So this could be the Liouville equation if you're dealing with a Newtonian system. It could be the Fokker-Planck equation if you're into stochastic dynamics. So this is a differential operator, this omega. And then formally you can solve this. And the formal solution is written here. Never mind for the time being the fact that, I mean, this looks like the differential equation for an exponential, but we have to be a little bit careful if the evolution operator is itself time dependent. So path ordered exponentials appear. But essentially the statement is that if I know the distribution function at some time t prime, I can integrate it up, at least formally, to obtain the distribution function at a later time t. And Matthias Fuchs and Mike Cates have used this, for example, to derive so-called generalized Green-Kubo relations, for example, to describe non-equilibrium averages of some quantity f. In the case of sheared colloidal suspensions, you would take the shear stress to obtain the stress as a function of time in a strongly sheared system. And again, formally, since basically, if you assume that at an earlier time, your system was in a stationary state, then and you apply a perturbation to your evolution at some time, then the formal solution that I just showed is easily rewritten in terms of this so-called generalized Green-Kubo relation. And I think I will skip the aside that I wanted to mention on active particles just in a few words, but it doesn't fit here at the moment. We've also been using this integration to transients approach to consider colloidal suspensions under different perturbations. But let's see what we can do with the quench. And my crude way of looking at this is as follows. Let's assume that up to time 0, we have the system in our initial configuration. So its dynamics is also described by some initial version of the Liouville-Osmolowski operator. And then suddenly I switch to something different. This could be a rapid quench in a confining potential, or it could be something else that suddenly changes the state of the system. And then we're interested in what happens at the time t larger than 0, which is our waiting time. So inserting this very simple-minded switching between one dynamics and the other dynamics at time 0 into the integration to transients formula, you get what is in the blue box here. This is now saying, okay, assuming that I'm going infinitely far out in time here, then I'm asking what is the final state probability distribution function that the system will reach. Given that it has a certain probability function at time tw, and then, as I said, it's just an application of the general formula that I just had on the slide, this is what you get. And this is still complicated to solve because, I mean, what I want to do is to basically solve this for P of TW, because then we would know the waiting time dependent distribution function of the system, assuming that we have an idea of what is the one in the final equilibrated state, which could be, for example, the Boltzmann one corresponding to the final state that we quench to, but might never reach. The problem is, of course, that here you still have a differential operator that acts on this thing, so this is not easy to back out. And now you see there's a little bit of space here. So now the crudest thing I could imagine doing is approximating whatever happens here by its projection onto some relevant variables. And it turns out if you just by hand say I'm only asking about the projection onto density pair fluctuations at a given waiting time TW, then you basically, this is why I call this a splitting approximation. You split the difficult problem into 2. And what you get is essentially what is here in the blue box. Or you can also look at this equation where I formulated it out. If I then take the previous equation here to evaluate the static structure factor, I would do that by integrating the probability distribution function with the square of a density fluctuation. So I get the structure factor in its final state minus the structure factor at waiting time TW, and then I get this complicated integral. But since in my approximation I split in the integral into 2 terms, I can rearrange and I get what is in the blue box, which is a deceptively simple looking equation. And it's basically the equation that Magdaleno will show to us in a bit, I would claim. And what it says is that the structure factor evolves towards its final state in a fashion that looks rather exponentially, because there's just a factor that corresponds to 1 over a relaxation time here. But the interesting thing in this equation is this relaxation time in turn is determined by the waiting time dependent dynamical structure functions. You can actually approximate this in the mode capping sense as the integral of, I'm sorry, of the transient density correlation functions. So this simple-minded equation will allow for 2 very different regimes. And this slide is virtually taken or stolen from one of Magdaleno's talks, where he presents it in a very similar fashion. He says we have exponential relaxation towards a final state. And 2 things can happen now. If we ask, when do we reach a stationary state, where the left-hand side should be 0, then either of the right-hand side terms has to be 0. So either we've reached the final state, which happens if the relaxation times remain finite. So in other words, it will happen if we quench to states that are not yet in the glass. Then we get equilibration, and in the end, nothing depends on the waiting time anymore. And That's the first set of solutions that we saw from the computer simulations. However, if this term goes to 0, so if the relaxation time diverges, there could be different solutions to the equation. And I will be brief because Magdaleno will explain to us more carefully. Now, if you look at this, or at my way of writing the relaxation times, what we actually need in order to calculate this relaxation time that enters here, we need to have a theory of the dynamical density correlation functions. And as you can suspect, I'm tempted to use MCT for that. So in the usual way, you go through the Moritz-Wanzig derivation of mode coupling theory, which I don't dwell upon here, just to show that it actually works also for these transient correlation functions that are defined with the waiting time dependent average all the time. You get the Moritz-Wanzig equation of motion with the memory kernel, and the memory kernel is approximated as a quadratic functional of the density correlation functions. So this is standard mode coupling theory, except that here everything depends parametrically on the waiting time, because all the averages I'm taking are averages defined as averages with the probability distribution function at a given waiting time. And as you also all know, the mode coupling equations, these ones under certain conditions can be solved asymptotically, analytically, which leads to the beta scaling equation that Tommaso built upon in his talk. So I jump right to it. So in the beta scaling regime, the density correlation functions can be written as the plateau value plus an amplitude times the square root of a distance parameter times a universal scaling function, the beta correlator. And this is the standard version that Tommaso also alluded to. And I just wanted to bring it up again to remind everyone that out of this, you back out the known asymptotic scaling laws of mode coupling theory. So the famous von Schweidler law, the critical decay law, T to the minus A, and in the end, also the fact that MCT predicts a power law like divergence of relaxation times comes all out of this equation. Again, as a reminder, this is how MCT looks for the hard sphere system. Those are the correlation functions calculated within MCT for various densities. And the beta correlator basically describes this regime power law decay towards a plateau and then power law decay from a plateau. And there are two diverging timescales involved here. And I wanted to remind you that the final timescale, which is asymptotically proportional to the alpha or structural relaxation timescale, is predicted to diverge as the distance parameter to the power of minus gamma, where gamma is an exponent that MCT can calculate. Now, as I said, I wanted to combine this with the non-equilibrium theory of aging that Magdaleno proposed. So we go back to this equation for the static structure factor, and we make use of the fact that close to the glass transition, the structure factor remains completely regular and boring. And so that means I can Taylor expand the structure factor. And basically all that should matter is that this is a regular function of the distance parameter. So it's next to leading, I mean, after the constant, it will be proportional to sigma and an amplitude that depends on the K vector. And again, this is the mode coupling factorization theorem in disguise. So there's only one scalar parameter that is relevant in describing what happens. So in the end, we can get rid of the K-dependent evolution here, and we can read this as an equation that tells us about a waiting time dependent distance parameter and an evolution of this distance parameter. So inverse tau will depend on the distance parameter at TW, and this will turn into sigma at TW minus the final sigma where we quench to. So this is what we set. And now we just have to solve this equation. But now it's easy because I just reminded you that for the relaxation time tau, we have a power law that is the asymptotic prediction of mode coupling theory. So this is a power law, and these are just linear terms in sigma. That's easy to solve. And so here it is again, the equation. Here's the power law again. The peculiarity that for positive distance parameter we are in the glass, the inverse relaxation time is 0 according to ideal MCT, and otherwise it's the inverse is minus sigma to the power of gamma. And then if you plug this in, you can actually play around a little bit with the balancing, and you discover that there are basically 3 regimes. The first one is easy, and I'm sorry, there's still a typo on these slides. So if the final point that you quench to is still in the glass, so this is a not too small negative value, then you can convince yourself that finally you will approach a solution where tau is a constant. The 2 interesting cases are if you consider this term that you quench to either large or small compared to the waiting time dependent sigma. And this basically distinguishes of whether you quench too close to the glass transition or you quench to a state that is very deep in the glass. If you quench into a state that's very deep in the glass, sigma f will be much larger than the typical sigma of TW. And if you then balance the powers, you discover a rather interesting prediction that the structural relaxation time is predicted to depend on the waiting time to the power of gamma divided by gamma minus 1, where gamma is the exponent of MCT. So this is the equilibrium exponent, and out of this you get a scaling law for the non-equilibrium evolution of the relaxation time. If you quench exactly to the glass transition, you can set this final term to 0, and then it's even easier to solve the equation. And you see that finally the relaxation time is predicted to grow just linearly with the waiting time. So you can call this normal aging, as it has variously been done in the literature. And if you work out the MCT exponents gamma, you discover that this exponent here that we get for quenches deep into the glass is larger than 1 always. So you can call this hyperaging or whatever. And again, that's a term that has been used variously. And this is then what the theory predicts. And what I show you here is, again, as the symbols, the computer simulation results that I showed right in the beginning. So this is, again, simulations of a hard sphere-like system quenched from some initial packing fraction to various final packing fractions, color-coded. And the solid lines are basically meant to emphasize the power law predictions that I just had on the previous slide. And what I did here is something that we like to do within MCT. We have the asymptotic solutions, but to get a little bit more than just the asymptotics, also some pre-asymptotic corrections, etc., you can build a schematic model that you tune to have the same power law exponents as the full model that you want to solve. So, and that's what I did here. I replaced the purely asymptotic solution with a simple-minded schematic model of MCT. And but I do show also the scaling predictions, which are the dashed and the dotted lines here. So reminder, the prediction is that for quenches right to the glass transition, we should observe normal aging, tau proportional to TW. And for all the quenches to states below the glass transition, we should observe eventually a constant, because the system equilibrates, and that's obviously observed and in agreement with the theory. If you look carefully or not too carefully in this intermediate regime between the 2 plateaus, you could try to describe this with an effective power law that would then have an exponent slightly less than 1, because the exponent 1 is the truly asymptotic solution that emerges, and you observe for all these others a crossover. And that is my current understanding of the sub-aging that has also been reported for various aging experiments in glasses, that is basically a crossover, because you cross over from something constant to something other constant on a log-log scale, and that looks like a power law. The truly new prediction, if you like, coming out of MCT combined with Magdaleno's theory is that there should be hyperaging if I quench to a state in the ideal glass. And for typical values of the exponents for hard sphere systems, you would get something like 1.68. And those are, the theory the schematic model agrees with its own asymptotic solution. So the theory shows this. Those are the purplish lines here. But then, of course, if you look more closely into the computer simulation data, what the purplish points do, they start deviating from this prediction rather early. So you might be skeptical of whether this hyperaging is a valid prediction that you should worry about, or whether it's just an artifact, if you wish, of the ideal glass state that you do not observe in simulations. And this is where now the stochastic beta relaxation theory will come in, because this hyperaging asymptote was calculated under the assumption that the relaxation time truly diverges at the critical point of node capping theory. And as we have learned from Tommaso, it doesn't. And let's see what the predictions will be. Just for completeness, I also show you the other plot that I also had in the beginning, where we fix the waiting time, and then we look at the relaxation time as a function of the density to which we quench, which I now represent as a distance parameter. So quenching to the critical density would be epsilon equals 0. Quenching into the glass would be epsilon larger than 0. And again, you see computer simulation and schematic model, and the lines more or less go through the data points, so we claim success. However, if you look carefully, and we can actually work out, well, this is the dashed line here is the known ideal MCT power law divergence at the critical point of MCT. So this is sigma to the minus gamma. And you can actually also work out asymptotic power laws for the evolution for quenches into the glass. And the only problem you need to see here is, again, this looks rather nice, but if you see the colors, actually the dark red data points should correspond to the dark red line of the theory. But they don't, they are much too low. And this is, again, the same problem that we are observing here, that the computer simulation data fall short of the divergence predicted by the ideal theory. So let's try to include fluctuations Tommaso style. So this is my one slide summary of stochastic beta relaxation. You've seen those plots, actually. You've seen this equation. And I just wanted to remind you of the two asymptotic predictions that Tommaso and I backed out of this equation, which relate to the structural relaxation time and the diffusion coefficient. And there's, if you like, a little bit of an additional ad hoc assumption where we say the structural relaxation time should be dominated by actually the average relaxation times of the system. Whereas, I mean, there's basically a distinction between the structural relaxation time and the mobility, where one is the mobility can be read of as the average mobility, whereas the relaxation time or the friction should be the inverse of the average. And the average of the inverse and the inverse of the average do not necessarily commute. And this is the reason why, as Tommaso, I think, also showed, the Stokes-Einstein relation is predicted to break down in the stochastic beta relaxation theory, because the product of d times tau no longer approaches a constant. And I've actually included this plot again. Tommaso has shown it. So this is the relaxation time as a function of the distance parameter from SPR. And if you work out the Stokes-Einstein relation, this is the typical plot that you do there. You plot the normalized diffusion coefficient as a function of the viscosity, and Stokes-Einstein would be a linear 1 over a viscosity law. And the theory predicts this to cross over to a fractional Stokes-Einstein law. I'm just showing this because there's by now also a nice fit to another two data sets of computer simulations that Hailong Peng calculated in a collaboration with us. So this works rather nicely. Now, what can we do with this plot? And again, unfortunately, the expressions here are a bit more complicated than the power laws. So the reminder is, if I go backwards again, all I need to do, in quotes, is to insert these asymptotic predictions here. And then I have an equation for the distance parameter sigma that I can solve asymptotically. Yet now this is a bit more complicated than the power law. but I can still do it numerically. And if I do that, basically nothing dramatically changes for the points where I quench to liquid states, because there in the end still ordinary MCT is good enough. But for the quenches into the glassy state, we get this. Of course, there are adjustable parameters here, as Tommaso was showing. So there's the delta sigma squared that you need to choose as an additional parameter here, essentially. But under plausible assumptions, you can make this work. And I think this is at least a qualitative statement that in principle, the deviations that we see here from the predicted hyperaging asymptote in the computer simulations can be explained by stochastic beta relaxation theory. And of course, since including fluctuations smears out the glass transition, there is no true divergence of the relaxation time anymore. And therefore, in all cases, we finally approach a waiting time independent stationary state. So if you see this, you could think that, oh, maybe this prediction of faster than waiting time aging was kind of fancy and nice. And I quite liked it when I first saw that this comes out of MCT. But apparently it's not really seen in real life. But I think maybe it is. And the way to see this should be by checking whether somewhere in here we still have a superlinear growth of the relaxation time. And of course, what we can do is we can divide the relaxation time by the waiting time. And then if we get something that grows as a function of waiting time, this indicates a superlinear growth of the structural relaxation time. So this is what I've done here. This is the structural relaxation time divided by TW as a function of TW. And again, the colorful symbols are all computer simulation results from papers co-authored with Magdaleno, I think, from various people in the audience here. And the lines are 3 examples of the combination of the non-equilibrium Langevin equation theory with the scaling laws of stochastic beta relaxation theory for quenches to a state into the liquid in red, to a state in the ideal glass in purple, and to a state at the critical point in yellow, where the ideal MCT prediction would be that the waiting time always grows linearly with the waiting, the structural relaxation time grows linearly with the waiting time. So this ratio should approach a constant. This is ideal MCT. And including fluctuations cuts off this constant and eventually causes a decay because the structural relaxation time eventually saturates to a finite value. And interestingly, I think even in the computer simulation data, you see some indications of a non-monotonic behavior. So you see a part where this ratio grows with a function of TW, as a function of TW. So this would be a short remnant of hyperaging. And then eventually this is cut off by fluctuations as described by SBR. And that's basically the story I wanted to tell. I have been looking a little bit in the literature about observations of such hyperaging regimes. And I didn't find many good data, not in structural glasses. I found a few in gels, and the solid data is basically I'm showing you this slide to say you have to believe the authors, because it's all in this inset here where they show the relaxation time as a function of the waiting time. And now you have to zoom into your zoom window to see whether this is linear or slightly superlinear. And the claim in the paper is it is. Also here, you have to go to the original references and blow up the PDF by 400%, and then you can perhaps see it. So I think there would be further room for experimental or computer simulation support of this. And with this, I would conclude. What I tried to summarize is that I think by combining the various approaches, I tried to basically re-establish Magdaleno's non-equilibrium evolution equations for the structure factor in a spirit that I took from the integration to transience formalism that Matthias and others have popularized within MCT. And if we then combine it with the scaling laws, in particular Tommaso's theory, we can come up with non-equilibrium scaling laws that very nicely describe the emergence of normal aging, sub-aging, and hyper-aging, with exponents that can be calculated from the equilibrium exponents, the equilibrium scaling laws of MCT, and they can even include the effect of quenches into the glass that cut off the hyper-aging asymptote by something finite. There would be a lot of things to do as future work we can discuss, but with that, I would just stop here and like to thank you for your attention.
Thank you very much, Thomas, for your very nice contribution. I think we have exceeded a little bit the time limit, and I will suggest to go directly to Magdaleno's presentation. I do have a couple of questions, comments. I'm very sorry. But I will suggest to move forward to Magdaleno's talk.